I'm Tomaso Poggio, and I will speak about the science and engineering of intelligence. Intelligence is one of the great problems in science. I personally think the greatest of all problems such as the origin of life, the origin of the universe, the structure of space and time. I think if we can make progress on the problem of intelligence, make ourselves more intelligent or make machines that help us think better, then we can more easily solve all other great problems of science and technology. And so that's why I think this one, the problem of intelligence, is the greatest problem. I want to speak about recent success stories of AI. I want to tell you where we are in solving eventually this problem of what intelligence is and how to make intelligent machines, tell you where AI may go next, and then speak about some interesting theoretical puzzle of deep learning, which is really at the core of the recent success stories in AI. And from there, speculate about what evolution could have discovered when it invented human intelligence. All right, so let me start with success stories of AI. In the last 25 years, AI and especially machine learning have made considerable progress, especially in the last decade. And two of the major success stories are AlphaGo. This was developed by DeepMind, started by Demis Hassabis here on the left. And the other one is Mobileye, who is now part of Intel and which is was funded by Amnon Shashua on the right side of the slide. These are the success stories of two postdocs of mine. And of course, I'm very proud of them. The first one, Demis showed through AlphaGo that machine learning can learn to play games such as chess or Go and be much better than human champions at them. So AI definitely is beating humans in the virtual world of games. The second success story is Amnon Shashua. He started Mobileye in Jerusalem, and Mobileye is a leader in developing autonomous driving system with vision. And that story shows that machine learning can copy intelligent behavior of humans in the real world of driving a car. The point I want to make here is that at the core of these success stories, there are two key algorithms of modern machine learning. One is reinforcement learning, and the other one is deep learning. Both DeepMind and Mobileye use both of them. DeepMind is emphasis is mostly on the reinforcement learning, and Mobileye more on the deep learning, but both these algorithms are key to their success. And just to tell you, this is a kind of parenthesis that I'm opening here. More than 25 years ago, we developed in my group at MIT a system that could be trained by machine learning techniques with images of pedestrians in order for the system to learn to alert a driver if there was a pedestrian crossing in front of the car. And this is a short video of a Mercedes in Ulm. This was a project with Daimler. So from a Mercedes in Ulm, the Mercedes 95 had the trunk full of computers, PCs actually, and you can see that it does a pretty good job at detecting pedestrians, though there are a couple of mistakes, like a traffic lights detected as a pedestrian. In fact, we had one error every 10 frames, which at the time was a pretty good result, but also meant 3 errors per second, which implies that such a system could never be used because you have 3 errors per second. Now, this compares with about 1 error every 50,000 kilometers of driving in the current Mobileye system. So this is about an improvement of a factor of 1 million over 20 years or so, which corresponds to about doubling, a bit less than doubling accuracy every year for 20 plus years. So that's the reason why machine learning is ready today for so many applications. This is the reason why machine learning has become so important for companies like Google and Microsoft and Amazon and Facebook and so on. All right. Now, despite all of this, despite all this recent progress, the problem of human level intelligence is not solved by a large margin. We still don't know how to build a robot that can be reasonably good, even just compared to kids without any particular training in terms of how they manipulate things, or even babies. They're essentially quite a bit better of our robotic machines for various reasons. Okay, so the question is, what is next in the science and engineering of intelligence? Clearly, there is a long way to go. And one of the things that I will ask is, how do we solve the problem of intelligence? Where are the next breakthroughs going to happen? My personal bias is that the past history, the brief past history of machine learning, tells us that the main breakthrough of the past came from neuroscience, and so I expect that several of the breakthroughs of the future will come from neuroscience. In fact, if we look back and we look at reinforcement learning and deep learning, in reinforcement learning, as I said, it's at the core of the algorithms used by AlphaGo. Deep learning is the core of many supervised learning algorithms that can classify different images and sentences and enable Alexa to understand speech. If we look at the history of these two algorithms, they both came from neuroscience. Reinforcement learning came from work in behavioral neuroscience, back to Pavlov, and deep learning came from the physiology of visual cortex, from work of David Huber and Thorsten Wiesel at Harvard. They recorded from neurons in the visual cortex of cats and monkeys and proposed an architecture for visual cortex that is essentially the architecture, not the training techniques, but the architecture used by deep learning networks, even a recent one like ResNet. So So this is the reason why in the Center for Brains, Minds and Machines, of which I'm the director, our focus is in understanding how the brain creates intelligence. And so this is the science of intelligence. I always remember that Francis Crick, of whom I was a good friend, with Jim Watson, one of the discoverer of the structure of DNA in '53, he insisted that the word science means natural science. So the object of science is chemistry, sciences are chemistry, physics, biology, astronomy, whereas machines are human artifacts that are parts of engineering. And so just keeping this distinction in mind, when I say science of intelligence, I really mean understanding how the brain and human intelligence work. When I say the engineering of intelligence, I mean the mathematics and the engineering that we require to build intelligent artifacts. And CBMM, the Center for Brains, Minds and Machines, which is based at MIT but comprises other universities like Harvard and Rockefeller and Johns Hopkins, is focused on the science of intelligence. And so the main goal of it is to understand how the brain and the mind work, and possibly from this understanding, developing more intelligent machines. So that's the mission of the center. And whether the intelligent machines, when they emerge, finally will come from our understanding of the brain, or they will be created by engineers independently of neuroscience, that's an open question. I believe that in any case, we still need to understand our intelligence and how it's created by the brain, in the brain. But whether intelligent machines can be made without neuroscience, quite possible. It's an interesting race to observe. It will take, for sure, I think, several decades. As a small advertisement in my talk, I want to mention that one of the most successful activities of this center, in addition to research and publishing many papers, but has been this summer course of Woodsole, in which we had great applicants from all over the world, working for 3 weeks, listening to lectures by our faculty, but working for 3 weeks on original projects, research projects, and really creating a community of scholars that can speak the language of machine learning and the one of cognitive science and the one of neuroscience. So a new generation of scientists in the science and engineering of intelligence. We're trying now to continue this Center for Brains, Minds and Machines. Maybe it will become an intelligence institute at MIT. And we are looking for funding beyond the NSF, the National Science Foundation funding that has maintained it until now and will until 2023. It's a basic curiosity-driven research. I think personally it will be, in any case, a key foundation for future progress in engineering. So now, let me tell you briefly about the puzzles of deep learning. It's something I've been working on for the last several years. And this is, if you know a bit about machine learning, has to do with one of the strange properties of deep networks, which is that they have many more parameters than training data, typically. And so this is kind of quite different from the statistics I learned in when I studied physics many years ago, where I was told that if you have a model and you want to find the value of some of the parameters, you better have twice as many data as parameters, maybe 10 times is better. So, but neural networks seem to defy this common wisdom and actually do with fewer data than parameters. Okay, so let's see what's going on. In deep network, you have these layers of neurons, and each neuron is summating a large set of inputs. Each one has certain weight, so this weighted sum is of course a number, and that is then passed through a nonlinearity, which is shown here, it's just a rectifier, and that's it. And this operation is repeated in each neuron at each layer for all the layers. Now, the key part of training such a computational machine is to find the right values of the parameters. And the parameters are these matrices of weights. So matrices, one matrix for each of the layer, and there may be many layers, and you have to find the value of these parameters. How do you find them? Well, you want to find them in such a way that they minimize some measure of discrepancy between the correct prediction that you want from the network, from the data for each set of data, and the true answer that you know under the form of a training set, in which for each input xi, each vector of inputs can be an image, you have an output zi, which is, for instance, a label of what is in the image. And you're minimizing, for instance, the square loss summated over all the elements of the training set by gradient descent, or more practically using stochastic gradient descent, in which this loss is not the sum over all examples, but each is the sum over a random subset of the example, which changes at every iteration of gradient descent. Okay, gradient descent is impressively successful, and in what I want to describe to you is a situation in which you are looking at the square loss. So the network is G, and this is the output of the network that I assume as scalar output. The training data is a binary classification problem for simplicity, in which the yi are +1 or -1. You have that the number of weights is much larger than the training set. And under these conditions, we want to study what's happened when gradient descent is used, as it is used today. And today, people use gradient descent with a couple of additions, one of which is so-called batch normalization that keeps the Frobenius norm of the weight matrix equal 1, unit norm at each layer during the iteration of gradient descent. And another one is a regularization term called weight decay that try to keep the total norm of the network. So this is the rho is the product of the Frobenius norm of all the layers to keep it small. Now, we model this by using Lagrange multiplier and therefore changing the loss function into this other form, in which we have a constraint of nu such that each of the vk is 1, and lambda is given as the weight decay parameters. If we study gradient descent on this loss function, we have a gradient flow that is, we can now write in terms of the time derivative of rho and the time derivative of the v. The matrix is V. And then there are a couple of interesting observations that the critical point of this dynamical system, the ones for which rho dot is equal 0, V dot is equal 0, are determined by the equilibrium value for rho, because for each rho, I have at least a critical point of the V, because the domain of the V is compact. And so, so this is given by this expression, and this means that the rho will, for very small lambda, will really be the same as maximizing the minimizing rho will be the same as maximizing the margin, defined in this case as the sum of yn fn. Notice that yn fn, if fn has the correct sign, all of these are positive, because the product yn fn when fn has the same sign as yn is always positive, and yn is +1 - 1. And so there are a few interesting consequences of this analysis. One is that the smallest rho, the solution with the smallest rho, are the minimum norm solutions, and they have the best margin. The best margin is essentially the largest f of xn for all xn, which typically correspond to good generalization. And then we find that that we have convergence to the minimum norm solution independently of initial conditions. And furthermore, and we'll see in a second, there is another interesting property that at equilibrium, all the margins are the same. And this is one of the key properties of what has been called the neural collapse, which is a set of phenomena that has been found by a Stanford group to hold at convergence for many different architecture of neural networks and for many different data sets. This seems to be a good characterization of how deep networks converge and what are the properties at convergence. And we also know that, although I did not write it here, oh yes, I did, so that this minimum norm solution are the ones that have the best but unexpected classification error for when you are comparing different solutions for the same network and data sets. So this is roughly pretty good characterization of convergence and generalization of deep networks. The fact that this is for the square loss is interesting because it makes previous results for the obtained with the cross entropy much cleaner, and we know empirically in the meantime that square loss is actually as good as cross entropy in classification problem. That's somewhat surprising. All right, so these puzzles are beginning to be solved. The puzzles in the mathematics of deep networks. What, of course, remains is to understand, how what is missing from in deep networks to go from there to real intelligence. And so the question is, from the point of view of the science of intelligence, the question is, what are the circuits that are really underlying human level intelligence? Are they in the brain? How evolution discovered them? What is this discovery? What is the key here? And I want to go back to some work that was done more than 50 years ago. And this was proposing neural networks, early neural networks, mimicking properties of so-called holographic memories. These networks were called associative memories, and they were developed to be able to store the association of a set of inputs, say vectors xi, with outputs vectors yi, in such a way that when I input again, after storing this association, I input again xi, I get out yi. David Wishaw and Christopher Longe-Higgins designed this network. They're actually not very different from networks of today. Networks of today are really dealing with the problem of generalization for new inputs X that are not among the ones used in the training set, so stored in a network, whereas the focus at the time was the memory one, was not the generalization one. But in fact, these networks, like the more modern ones, can be memories, but can be also generalized. And we can see this considering standard supervector machines or radial basis function networks that are the solution to a minimization problem of this type, and are equivalent to one hidden layer networks in which each of the units is centered in one of the example xi, and so the output of each unit is the value of k at center xi for the input x. And for instance, if k is a Gaussian and the Gaussian has a very small sigma, then this k is essentially a delta function centered in xi, and the output will be yi, provided that x is very close to xi. So this is really a lookup table, an associative memory like the one devised by Christopher Longe-Higgins and David Wishaw. And if the sigma of the Gaussian is larger, then an x which is close to xi but not very close will provide an output. So this is the case in which the network will generalize, will interpolate between input example. But, from a certain point of view, the networks of today, and this argument also holds, at least to some extent for deep networks, they are lookup table, essentially. They're a bit more than lookup table because they can generalize, they can interpolate, but they're essentially big associative memories. And so it seems likely that there are many aspects of our intelligence cannot be explained just in terms of big associative memories, in part because we do not to be trained to solve many problems with a lot of training data like these networks are. And so the explanation in terms of a big associative memory does not seem to be powerful enough to explain human intelligence. So what else could evolution have found? Well, evolution could have found a couple of tricks to go beyond associative memories. One is the simplest, most natural one is that it could have invented circuits that are similar to a Turing machine, in which, yes, there is an associative memory, but essentially that's the program which associates for each input and output. But then there is also an association of, through this associative memory, given a state, a successor state of the system. And so in this way, you have a computational system that is much more powerful than a lookup table or an associative memory. It's Turing machine is a universal computer. So the discovery of evolution from the point of view of neural circuits could have been recurrence for hidden state and recurrence for input and outputs. That's not the full explanation, but maybe the beginning of looking at how evolution could have discovered circuits in cortex that are capable of processing different type of inputs, from visual inputs to acoustic to language, in a very powerful universal way. There are, of course, related open questions. For instance, the programs running these machines, these Turing machines, how were they, how were stored, how did evolution discover and evolve them? Let me stop here. This last part is very speculative, just a set of almost random association, if you want, but I hope that gives you some context to framing the problem of intelligence and what are we dealing with and where we are in making progress, and eventually solving it and finding out how our brain makes intelligence. Thank you.